650 light-years away, a star the size of the entire inner solar system is keeping a secret, a rather large one. For over a century, astronomers were convinced it was dying alone, a giant burning through its final fuel in quiet, lonely silence. They were wrong. A companion star called Sawara is trapped inside it right now, spiraling inward through thickening gas, and the collision it is heading toward cannot be stopped. Not slowed, not reversed. The process has already passed the point of no return, and an irreversible merger that could trigger one of the most violent explosions our galaxy has ever produced is unavoidable. Stay with me, because tonight we follow that descent all the way to the end. If you are new here, welcome to the channel. Get comfortable and stay until the end, because what we are about to walk through is genuinely one of the strangest confirmed stories in modern astrophysics. A star you can see with your naked eye is not what anyone thought it was. It is a system that crossed its own tipping point long ago and has been quietly, measurably, descending towards something enormous and violent enough to potentially reshape an entire corner of the galaxy. And it only gets more interesting the deeper we go. Now, let us get into it. Part 1. The tipping point. There is a second star inside Betelgeuse, and it is falling. Not orbiting around it the way planets orbit a sun, not drifting nearby in some comfortable gravitational dance. Inside. Physically submerged inside the atmosphere of one of the largest stars visible to the naked eye, spiraling inward through thickening gas, losing energy with every single orbit, accelerating toward a collision it cannot escape. And the process has already passed the point of no return. Step outside on a clear night, face south, find the constellation Orion, and look toward the upper left. That reddish-orange star, the one that looks almost warm compared to the blue-white glitter around it, that is Betelgeuse. It sits roughly 650 light-years away, which sounds impossibly far until you realize that on the scale of our galaxy, it is practically next door. It is so close that astronomers can actually resolve its surface, not just detect it as a point of light, but image it, watch it pulse, watch it dim, watch it do things that stars of its size should not be doing. And for most of the last century, the story of Betelgeuse was a straightforward one. A massive star, somewhere between 16 and 19 times the mass of our Sun, burning through its nuclear fuel, swelling into a red supergiant, and slowly, inevitably, marching toward a supernova explosion. A lonely death. A single star meeting its end the way most massive stars do, alone, internally. That story is wrong. What astronomers have been piecing together over the last several years, through reanalyzed archival data, through spectral measurements, through interferometric imaging, and through two independent research teams arriving at the same conclusion, is that Betelgeuse is not dying alone. It is locked in something far stranger, far more violent in slow motion, and far more consequential for how we understand stellar death. There is a companion object inside its atmosphere. A star roughly 1.5 times the mass of our Sun, referred to in the research community as Sawara, embedded inside the extended outer envelope of Betelgeuse, dragging through stellar gas with every orbit, converting its own orbital energy into heat, sinking deeper and pulling the entire system toward an irreversible merger that could reshape the final explosion. The word tipping point gets used loosely in a lot of contexts, but in orbital mechanics, it has a precise and brutal meaning. A tipping point is the threshold past which a system cannot recover. There is no restoring force. There is no equilibrium to return to. The feedback loop takes over, and the outcome becomes inevitable regardless of what happens next. And what the physics of this situation tells us is that Sawara crossed that threshold. It is already inside the envelope, the drag is already active, the orbit is already shrinking, and every meter it descends, the gas around it gets denser, which means the drag gets stronger, which means the orbit shrinks faster, which means the gas gets denser still. This is not a metaphor. This is the mechanism, and it is happening to a star you can see with your own eyes tonight. Now here is something worth sitting with. The estimated timescale for this merger to complete is roughly 9,000 to 10,000 years. On a human scale, that is an eternity. But on a stellar scale, it is nothing. Our Sun has been burning for about 4.5 billion years and has roughly another 5 billion to go. Betelgeuse itself has existed for around 8 to 10 million years. 10,000 years in that context is not a long death. It is a blink. It is the last exhale before the collapse. And the reason this matters, the reason this changes things well beyond a single, interesting star in Orion, is that Betelgeuse may not be an unusual exception. The signal that gave away this companion, the orbital fingerprint embedded in decades of brightness measurements, had been sitting in the data for over a century. Astronomers had seen it and explained it away with other models. They had looked directly at the evidence of a hidden star inside another star and interpreted it as something mundane. So the real question this opens up is not just about Betelgeuse, it is about how many other stars we are misreading right now. But before we get to that, we need to understand why the signal was there all along, and why it took us this long to actually hear what it was saying. Part 2, the signal we misread for 100 years. Betelgeuse pulses. That is not surprising. Red supergiants of its size and mass are expected to expand and contract in rhythmic cycles, driven by internal pressure fluctuations, the same way a giant's slow heartbeat. The primary pulsation cycle of Betelgeuse runs at approximately 400 days. About 13 months of slow brightening and dimming, consistent enough that astronomers have been tracking it for well over a century. But layered underneath that 400-day rhythm, something else was present. A second cycle, much longer, much slower, running at approximately 2,100 days. That is roughly 5.7 years, just under 6 years, repeating with a regularity that was hard to dismiss as noise. Astronomers noticed it. They named it. They called it the long secondary period, or the LSP, and then they spent decades arguing about what it was. The instinct, understandably, was to treat it as another pulsation, just a slower one, a secondary resonance in the internal structure of the star. But the problem with that explanation runs into hard physics. For a pulsation to operate on a 6-year cycle, the star would need to be physically expanding and contracting by an extraordinary amount. The changes in size implied by a genuine structural pulsation at that timescale simply do not match what is observed. The math does not work. You would need a star behaving in ways that models of red supergiant interiors consistently fail to produce. Other alternatives were tested. Convection was one of them. Red supergiants are known to have enormous convective cells on their surfaces, bubbles of hot gas rising and falling that can be as large as the entire solar system. These cells can create brightness variations, but the key word is can. Convection is chaotic by nature. It does not repeat on a clean 6-year cycle. It produces variations that are irregular, overlapping, unpredictable. Convection could mimic a period, but it could not produce the kind of strict repeating regularity that the long secondary period shows. Magnetic cycles were proposed, similar to the 11-year solar cycle that governs sunspot activity on our own sun. But in a star the size of Betelgeuse, magnetic cycles of that kind would need extraordinary field strengths, and the spectral evidence for those field strengths simply was not there. The magnetic cycle idea kept running into observational roadblocks. What nobody seriously entertained for most of this period was the simplest orbital explanation, that the 6-year cycle was not an internal property of Betelgeuse at all, that it was the orbital period of something moving around it, or more precisely through it. The periodicity of an orbit is governed by the mass of the central object and the radius of the orbit. Plug in Betelgeuse's mass and a plausible companion mass, set the orbit at a few astronomical units inside the extended atmosphere, and you get a period that falls directly into the range of the long secondary period. The signal fits. The physics fits. But the idea that a star could be orbiting inside another star's atmosphere, still on a gravitationally coherent path, without having been immediately destroyed, was uncomfortable enough that it kept getting bypassed. And that hesitation is understandable, because common envelope systems, which is the technical name for what we are describing here, are almost impossible to observe directly. They are short-lived on stellar timescales. They are optically obscured because the companion is buried inside the luminous envelope, and the evidence for them comes primarily from the aftermath, rather than the event itself. Most of what we know about common envelope evolution comes from modelling systems that have already completed the merger: neutron star binaries, certain types of supernova, the compact remnants of stars that clearly did something unusual before dying. But here is the thing about that long secondary period. It did not go away. It persisted across decades of independent measurements. It showed up in visual brightness data, in infrared, in radio. Every time someone looked at Betelgeuse over a long enough baseline, the 6-year rhythm was there. Patient, regular, waiting to be correctly interpreted. It was the first footprint, and the star that left it was already falling inward. Part 3. The moment everything broke. 2019 to 2020. In late 2019, Betelgeuse started doing something alarming. The star, which had been reliably bright for as long as human civilization had been watching the night sky, began to dim, not slightly. By January of 2020, it had faded to roughly 40% of its normal brightness, dropping far enough that casual observers could notice without any equipment. It went from one of the 5 brightest stars in the night sky to something almost forgettable in Orion. The internet had opinions. Headlines ran with the supernova angle. This was it. The prediction was finally coming true. Betelgeuse was about to explode. Astronomers tried to be measured about it publicly, while internally mobilizing every available telescope to collect data as fast as possible. The actual explanation, when it came together over the following months, turned out to be neither a supernova nor a structural collapse. What had happened was a surface mass ejection, a violent outburst from the photosphere of Betelgeuse that launched a significant cloud of material outward. As that cloud cooled and expanded, the solid particles within it, silicon and iron compounds condensing from the ejected gas, blocked the starlight reaching Earth. It was essentially a self-generated dust cloud, a star briefly hiding behind its own expelled material. Not a death, not a collapse, a belch. But the scientific importance of what happened next is easy to underestimate, because when every telescope on Earth and several in orbit turned toward Betelgeuse in a coordinated panic, they collected an extraordinary amount of high-quality data across multiple wavelengths. Spectroscopic measurements, interferometric images, ultraviolet monitoring from the Hubble Space Telescope, all of it gathered in a compressed time window with unprecedented resolution and coverage. And that data did not just confirm the dust cloud explanation. It became a resource, a baseline of extraordinary detail against which future observations could be compared. And when astronomers later went back through that data, looking not for signs of collapse, but for signs of something orbiting inside the atmosphere, the information they needed was already there. The Great Dimming did not reveal Su'a directly, but the observational surge it triggered created the dataset that would eventually help confirm the inspiral. It was an accident that became an instrument. The noise of a surface eruption that generated the clearest signal yet of something moving through Betelgeuse's atmosphere in a pattern that pulsation and convection alone could not explain. The star was already in motion, and the next question was, what was pulling it? Part 4. The discovery nobody expected. 2 independent research teams working with overlapping but not identical datasets arrived at the same unexpected conclusion around the same time. Betelgeuse was wobbling. Not wobbling in the way a top wobbles when it starts to slow down, not a precession of its rotation axis, wobbling in its position on the sky. A subtle rhythmic shift in the star's apparent centre of light, repeating on a timescale that matched the long secondary period almost exactly. 6 years. the same 6 years that had been sitting in the brightness data for over a century. In planetary science, stellar wobble has been a detection method for decades. When a planet orbits a star, the gravitational pull is mutual. The planet does not just orbit the star also orbits the common center of mass of the pair, producing a tiny rhythmic motion that can be detected in precise spectroscopic measurements. This is how hundreds of exoplanets have been confirmed without ever directly imaging them. You infer the planet from the star's response to it. The wobble detected in Betelgeuse follows the same logical structure, but with a critical difference. The object causing the wobble is not orbiting outside the star at some comfortable distance. It is orbiting inside the atmosphere, and at a mass of roughly 1.5 to 1.7 times our Sun, it is not a planet, it is a star. Embedded in the extended diffuse outer layers of one of the largest stars in our galactic neighborhood, dragging through the gas on every orbit, losing energy, sinking deeper. The name chosen for this companion, Siwaha, comes from astronomical convention and carries with it a certain appropriateness, given that it will ultimately not survive its relationship with Betelgeuse. It is named for the orbital partner whose fate is already sealed by the medium it is moving through. In 2025, a team using the Gemini North Telescope deployed speckle interferometry, a technique that reconstructs high-resolution images from rapid sequences of short exposures, to search for a faint secondary signal in the immediate optical vicinity of Betelgeuse. What they found was a faint excess of light near the predicted orbital position of the companion. The statistical significance of that detection sits at approximately 1.5 sigma, which, in terms of scientific certainty, means it is suggestive rather than definitive. It is not enough to put on the wall and call confirmed, but it is consistent with every other line of evidence: the wobble measurements, the long secondary period, the orbital predictions, the atmospheric disturbance patterns. What we are dealing with is no longer a hypothesis that lives only on paper. It is a working model supported by multiple independent lines of evidence converging on the same answer. Betelgeuse is a common envelope binary, 2 stars sharing one outer atmosphere, one of them still coherent and orbiting, the other surrounding it on all sides, and the one on the inside is falling. That falling is not a future possibility, it is the current state, which means that what we are trying to understand now is not whether this is happening, but what the physics of that fall actually looks like, and how far it has already gone. Part 5. Meet Siwaha, the star inside the star. Let us try to actually picture this, because the geometry of it is unlike anything intuition prepares you for. Siwaha is estimated to be somewhere between 1.5 and 1.7 times the mass of our Sun. That makes it, by any normal measure, a significant stellar object. If you placed it at the center of our solar system in place of the Sun, it would outshine everything else in the sky. It would be the dominant gravitational and luminous presence in our entire planetary system. It is not a dim brown dwarf, not a neutron star, not a black hole. It is a substantial, ordinary kind of star, and it is orbiting inside Betelgeuse. Betelgeuse has a radius somewhere around 700 to 800 times the radius of our Sun. If you placed Betelgeuse at the center of our solar system, its outer layers would extend past the orbit of Jupiter. The distance from the core of Betelgeuse to the outermost extent of its photosphere is larger than the distance between the Sun and Jupiter. And Siwaha is not outside this boundary. It is orbiting at approximately 4 astronomical units from the center of Betelgeuse. 4 astronomical units is roughly the distance from the Sun to the asteroid belt, the region between Mars and Jupiter. That orbit sits comfortably inside the extended body of the star. Now here is what makes this system physically survivable, at least for now. The outer layers of a red supergiant like Betelgeuse are extraordinarily diffuse. You could describe them as a very, very poor excuse for what we normally think of as stellar material. The density of gas in those outer regions is so low that in some parts it approaches what we would call a near vacuum by laboratory standards. We are talking about pressures far lower than the best vacuum chambers humans have ever built on Earth, just with enough material spread across a huge volume to hold together gravitationally and interact with light. This is why Siwaha has not been immediately torn apart or vaporized. It entered a region of the star where the gas is so tenuous that it can maintain a coherent gravitational identity. It is still a star. It has not been smeared into a debris cloud. But it is moving through a medium, and any object moving through a medium experiences drag. Think about the difference between walking through air and walking through water. You can move through air without much effort, but water pushes back against you with every step. Now imagine that the medium is not water, but an incredibly thin gas, except that you have to move through it continuously on an orbital path hundreds of millions of kilometers long. Even a small drag force, applied consistently on every loop of that orbit, removes energy from the system. Orbital energy is the thing that keeps Siwara moving fast enough to stay in orbit rather than falling straight inward. Remove orbital energy and the orbit shrinks. A smaller orbit passes through denser gas. Denser gas means more drag. More drag means faster energy loss. Faster energy loss means a smaller orbit still. This is the in-spiral, and it is already running. What it leaves behind with every orbit is a wake of disturbed gas, a turbulent trail of heated stellar material tracing the path of a star that is slowly, measurably, irreversibly falling toward the center of another. Part 6. Common Envelope Evolution. Explained simply. Common envelope evolution is one of those phrases in astrophysics that sounds technical enough to be safely ignored, which would be a mistake, because what it describes is one of the most transformative and poorly understood processes in the entire life cycle of stars. Here is the basic situation. You have two stars that were originally orbiting each other at a comfortable distance. One of them, the more massive one, expands dramatically as it ages. It swells into a red giant or a red supergiant, and it swells so much that its atmosphere engulfs the companion star before the companion can escape. Now you have a system where one star is physically inside the outer envelope of another, which is exactly the situation we're describing at Betelgeuse. The reason this phase is described as short-lived in stellar terms is that it is inherently unstable. The companion cannot orbit inside the gas envelope without friction. Friction takes orbital energy. As orbital energy is removed, the companion spirals inward. Meanwhile, the energy deposited into the envelope heats it, potentially causing it to expand or even be partially ejected. The system is always moving toward one of two endpoints. Either the companion gets all the way down to the core and merges, or the envelope is entirely expelled by the deposited energy, leaving the two stellar cores in a tight orbit. Both outcomes are dramatic. Neither involves the system staying the same. What makes Betelgeuse so scientifically important here is the combination of two factors. First, it is close. At 650 light-years, it is close enough that we can actually try to resolve features and measure motions with modern instrumentation. Most stars undergoing common envelope evolution are far enough away that they appear as simple points of light, indistinguishable from uncomplicated systems. Second, Betelgeuse is still in the middle of the process. We are not looking at a remnant of common envelope evolution, a neutron star with a white dwarf companion, a gravitational wave source that merged millions of years ago. We are potentially watching one of these systems in real time, with enough resolution to detect the signatures of the in-spiral while it is occurring. Common envelope evolution is believed to be a key step in the formation of the most energetic systems in the universe. Merging neutron stars that produce gravitational waves, double black hole systems, certain types of supernovae that are far more energetic than standard core collapse. The close compact binaries that astronomers detect with gravitational wave observatories are thought to have gone through a common envelope phase earlier in their evolution, when the stars were still ordinary. So understanding how the in-spiral actually works, how fast it proceeds, how much energy gets deposited into the envelope, what the drag forces actually look like, is not just about Betelgeuse. It is about improving models that connect to some of the most energetic phenomena in the observable universe. The problem is that simulations of common envelope evolution are notoriously difficult to run accurately. The physical scales involved are enormous. You have to model the orbit of a stellar mass object inside a gas envelope that spans hundreds of solar radii, while simultaneously tracking turbulence on scales many orders of magnitude smaller. The simulations exist, and they have become increasingly sophisticated, particularly a set of three-dimensional hydrodynamic models published in 2024 by Scheiber and collaborators. But simulations are not the same as observations, and Betelgeuse may be giving us for the first time something more valuable than a simulation. It may be giving us a real system, close enough to measure, while the in-spiral is still happening. That real-time observation is the thing that could finally close the gap between what the models predict and what actually occurs when a star starts falling through another star's atmosphere. Part 7. The feedback loop that seals its fate. Let us be precise about the mechanism, because the word in-spiral is easy to say and harder to feel the full weight of. What is actually happening to Siwaha step by step is a sequence of physical consequences, each one making the next one worse. Siwaha is orbiting at approximately 4 astronomical units from the centre of Betelgeuse. That orbit requires a specific velocity. To maintain a stable circular orbit at any radius, an object has to be moving at exactly the right speed, fast enough that centrifugal tendency balances gravitational attraction. If you slow it down even slightly, gravity wins just a little, and the orbit drops to a smaller radius. Now the object is moving through gas. The gas exerts a drag force, which acts opposite to the direction of motion, which means it takes velocity away from the orbiting star. Gravity wins fractionally, and Siwaha descends. At a smaller radius, two things change. The gravitational pull is stronger, requiring higher velocity to maintain orbit, and the gas density is higher, because the interior of Betelgeuse becomes progressively denser as you approach the core. Higher gas density means more drag. More drag means faster velocity loss. Faster velocity loss means faster orbital decay. The orbit is now shrinking faster than it was before, which means it will arrive at an even denser region even sooner, which means the drag will be even stronger still. There is no equilibrium in this sequence. There is no point at which the forces balance and the decay stops. Every step down makes the next step down happen faster. This is the classic runaway feedback loop, the kind that appears in engineering catastrophes, in ecological collapses, in any system where the corrective mechanism is overwhelmed by the destabilizing one. Picture dropping an object into a thick fluid that gets progressively thicker the deeper you go. At first, the descent is slow because the fluid near the surface is thin. But as the object sinks, it moves into thicker and thicker material, slowing ever further, converting its gravitational potential energy into heat in the fluid around it, until eventually it reaches a depth where the fluid is so dense that it can barely move at all. Except in this case, the object is not slowing to a stop. It is losing orbital energy, which means instead of slowing in a linear sense, it is spiraling faster and faster inward toward the core. The energy that Siwaha loses with every orbit does not disappear. Energy is conserved. It goes into the surrounding gas as heat and kinetic turbulence. The gas is being stirred, compressed locally by the passage of Siwaha through it, and heated by the friction of that passage. This energy injection is not trivial. Some models suggest it could contribute to observable effects in the outer atmosphere of Betelgeuse in the form of enhanced mass loss, asymmetric outflows, and turbulent fluctuations in brightness that would not be present in an isolated single star. This is precisely the kind of disturbed, energetically active behavior that Betelgeuse has been exhibiting. Not continuously exploding, not collapsing, but behaving in ways that are systematically different from what stellar evolution models for isolated red supergiants predict. And the in-spiral is still in its early to middle stages. The drag is stronger than it was 1,000 years ago. It will be stronger still 1,000 years from now. The fate of this system is not a question. The direction is locked. And the physics is already in motion. Part 8. The Wake. Proof in Motion. If Siwara is truly moving through the atmosphere of Betelgeuse, it should leave traces. A solid body moving through a fluid does not just pass through silently. It pushes material forward, leaves a zone of lower pressure behind, generates turbulence in its wake, and induces velocity patterns in the surrounding medium that persist long after the object has moved on. The question was whether those signatures would be detectable across 650 light-years. The answer, it turns out, is yes, or at least something that looks strongly consistent with that answer is present in the data. Ultraviolet spectroscopic data collected by the Hubble Space Telescope during and after the Great Dimming Period provided one of the most important datasets for this analysis. Ultraviolet light is particularly useful for probing the velocity structure of stellar atmospheres because it traces specific atomic transitions in elements like magnesium and iron that can serve as tracers of gas motion. When you map those velocities across the disk of Betelgeuse, you can build a picture of where gas is moving toward the observer, where it is moving away, and how those patterns shift over time. What the analysis found was a systematic asymmetry in those velocity patterns. One side of Betelgeuse's atmosphere showed gas being pushed in one direction, while the other side showed gas responding differently, and those patterns shifted in a way that correlated with the predicted orbital phase of the companion. This kind of asymmetric, phase-correlated atmospheric motion is sometimes called a dipole motion, and it is exactly what you would expect from a massive object dragging gas as it orbits through the medium. The analogy is a boat moving through water. The bow pushes water forward and to the sides. The stern leaves a turbulent wake behind it. If you could measure the velocity of every water molecule around the boat, you would get a complex but organized pattern tied to the boat's position and motion. Detecting something analogous in the atmosphere of a star 650 light-years away, using the Doppler shifts of ultraviolet spectral lines, is technically extraordinary. But the pattern is there. Ground-based observatories contributed additional independent measurements of the atmospheric velocity structure, and while no single observation constitutes a smoking gun, the combination of the wobble detection, the long secondary period analysis, the Gemini North imaging signal, and the Hubble ultraviolet atmospheric velocity patterns all point in the same direction. Something is moving through the atmosphere of Betelgeuse. It has the mass and orbital period consistent with a stellar companion at roughly 4 astronomical units, and it is disturbing the surrounding gas in a way that traces its orbital path. This is not a theory sitting on paper any longer. The wake of Siwara's passage is written in the motion of stellar gas around a star you can see from your backyard, and that motion is accelerating. Part 9. The spin that shouldn't exist. Here is a measurement that should not be possible, and yet there it is every time astronomers point their instruments at Betelgeuse and try to measure how fast the star is rotating. Red supergiants, by the time they have evolved to the state Betelgeuse is currently in, should be rotating extremely slowly. This is not a vague expectation. It follows from basic physics. As a star expands from a main sequence object into a red supergiant, conservation of angular momentum means that the rotation rate drops dramatically. The same reason a figure skater slows down when they extend their arms. A star expanding to hundreds of times its original radius is extending those arms by an enormous amount. The expected rotation rate for a red supergiant of Betelgeuse's age and mass is less than 1 kilometer per second at the equator. Betelgeuse is rotating at approximately 5 kilometers per second. Some measurements push that estimate toward 10 or even 15 kilometers per second. Even the conservative end of that range is 5 times faster than the theoretical maximum for a single, isolated red supergiant. That is not a small discrepancy. That is the kind of number that means something is wrong with the premise. The natural question is where all that angular momentum came from. In an isolated star, it has nowhere to come from. Rotation should only decrease as the star ages and expands. There is no mechanism within a single star to spin it back up. But in a binary system where a companion is orbiting inside the envelope, there is a mechanism. Orbital angular momentum can be transferred into the stellar envelope as the companion interacts with the surrounding gas. Siwara, spiraling inward through Betelgeuse's atmosphere, is not just converting orbital energy into heat, it is also depositing orbital angular momentum into the gas around it. That gas in turn interacts with the broader stellar envelope, and over time the rotation of the outer layers gets spun up in the direction of the orbit. This is, effectively, the star being stirred from the inside, not the core, the extended envelope being pulled and pushed by the passage of a star-sized object on its orbital path. And the measurement of enhanced rotation in Betelgeuse is consistent with exactly that process. Now, a fair caveat has to be acknowledged here. The rotation measurement in Betelgeuse is not unambiguous, because the alternative interpretation is annoyingly plausible. Betelgeuse has enormous convection cells. These giant bubbles of rising and falling gas can create Doppler shifts across the star's disk that mimic rotation. If one large convective cell is rising on one side while another is sinking on the other, the spectral measurement would show what looks like rotation, even if the star is barely rotating at all. Simulation studies suggest that convective effects could account for an apparent rotation signal in a significant fraction of measurement attempts under current resolution limitations. But here is the critical distinction. Convection changes. Convective cells form, rise and subside over timescales of months to years. A convective explanation for the rotation signal would produce a measurement that shifts, fluctuates, and behaves inconsistently over time. What you want to check is whether the rotation signal in Betelgeuse has persisted coherently across multiple independent measurements over different epochs. And even if it turns out that some portion of the apparent rotation is a convective artifact, the orbital wake evidence stands independently. The spin anomaly may or may not be real in its full magnitude, but the atmospheric disturbance patterns require a different explanation than convection alone. The inspiral is not dependent on any single measurement. It is the only model that accounts for all of them simultaneously. Part 10. Counter theory. Is it an illusion? The history of astronomy contains more than a few cautionary stories about a result that seemed almost certain until a better explanation emerged. And any honest account of the Betelgeuse binary hypothesis has to include the voices in the scientific community that are not convinced. The strongest counter-argument to the rotation evidence, and arguably to parts of the wobble detection as well, centers on the convective structure of the star. Betelgeuse is not a smooth sphere with a clean surface. It is a roiling, violently turbulent object with convective cells that can individually be the size of several hundred solar radii. When these cells are in motion, they create surface brightness asymmetries, which shift the apparent center of light of the star, which produces a wobble signal in astrometric measurements, which looks very similar to what would be produced by a companion object pulling the star gravitationally. Sophisticated hydrodynamic simulations of red supergiant convection have demonstrated that under the resolution limitations of current instruments, a single star with realistic convective activity could generate apparent astrometric wobbles and apparent rotational signatures that would be consistent with the binary hypothesis a significant fraction of the time. Some estimates suggest that well over half of similar measurements on a convecting single star would produce false positives for a companion. This is a serious objection. It means the wobble alone, or the rotation alone, is not sufficient to conclude a companion is present. The threshold for claiming a binary detection on the basis of astrometric wobble in a convective red supergiant is significantly higher than it would be for a quiet, stable star. The scientific community has not reached consensus. There are researchers who view the binary hypothesis as compelling and converging, and there are researchers who regard each individual piece of evidence as explainable by single-star physics. The debate is ongoing, active, and unresolved. But here is why the skeptical case does not cleanly dismiss the inspiral story. Convection cannot explain the long secondary period. Or more precisely, convection is not expected to produce a strictly repeating multi-year period, because convection is inherently stochastic. It generates irregular variability, not clean orbital signatures. The 6-year periodicity that has been present across more than a century of independent measurements is difficult to attribute to random convective activity, and the atmospheric velocity patterns detected in the ultraviolet data, the asymmetric gas flows correlated with orbital phase, are also not naturally produced by convection alone. The skeptics are right to push back on individual pieces of evidence, but the overall weight of multiple independent lines of evidence, each one consistent with a common envelope binary, and none of them fully explained by the single star alternative, keeps the inspiral hypothesis alive and arguably ahead. The 2027 observation window, which we'll get to later, may finally provide data precise enough to settle the matter. Until then, the debate itself is part of the story of Betelgeuse. Part 11. The star being stirred from inside. Imagine filling a glass with honey and then dropping a small marble into it. The marble sinks slowly, but as it moves downward, it drags honey with it. It creates a swirling column of disturbed fluid that extends both above and below it, pulling material in from the sides, leaving a chaotic zone in its wake and distributing its gravitational potential energy into the fluid as heat and motion. Now scale that marble up to 1.5 times the mass of our Sun, scale the honey up to the extended atmosphere of a red supergiant, and you have something approximating what Siwaha is doing to Betelgeuse from the inside. The energy that Siwaha deposits into the envelope with every orbit is not evenly distributed. It concentrates along the orbital path, creating asymmetric heating that preferentially affects regions the companion passes through. This asymmetric energy injection drives the development of asymmetric outflows, regions where the stellar wind is enhanced in one direction but not another, producing a non-spherical pattern of mass loss that would be measurable if you could image the immediate circumstellar environment of Betelgeuse with sufficient resolution. Some of that resolution is now becoming available. Interferometric imaging at millimeter and submillimeter wavelengths has revealed that the material immediately surrounding Betelgeuse is not symmetric. There are clumps, plumes, and asymmetric density structures in the circumstellar environment that have been documented across multiple observation campaigns. These structures are sometimes attributed to the convective ejection events that are certainly occurring, but their distribution and persistence are in some cases consistent with the kind of orbital phase-dependent mass loss enhancement that a spiraling companion would produce. The three-dimensional hydrodynamic simulations published by Scheiber and collaborators in 2024 are particularly relevant here. These models attempted to simulate the behavior of a common envelope system with parameters roughly matching the Betelgeuse-Siwaha hypothesis, tracking how the companion's orbital energy gets distributed through the envelope over time. One of their results was that a significant mass of envelope material, on the order of half a solar mass or more, can be ejected from the outer layers of the primary star through the energy injection process before the merger is complete. Not in a single explosion, but gradually, driven by the cumulative heating effect of the spiraling companion. Half a solar mass ejected from the envelope of Betelgeuse over the course of thousands of years would create a substantial shell of circumstellar material. And when Betelgeuse eventually does reach core collapse, either triggered by the merger or completing its natural nuclear evolution, that explosion will propagate outward into a medium that has already been significantly pre-shaped by the inspiral. The interaction of the supernova shockwave with that pre-ejected shell changes the observable character of the explosion, potentially making it brighter, more asymmetric, or longer lasting than a standard core collapse supernova in an unmodified environment. The star is being changed from the inside right now, not dramatically enough to see with the naked eye, but measurably, progressively, in ways that will determine how it dies. Part 12. The Great Dimming Connection. Revisited. The 2019 Great Dimming remains the best characterized surface event in Betelgeuse's recent observational history, and its primary explanation, a surface mass ejection followed by dust formation, is well supported by the data. A large convective cell near the surface produced an outflow of gas that cooled in the outer atmosphere and condensed into dust particles that temporarily blocked light reaching Earth. That sequence of events is not seriously disputed. What is more speculative, and worth flagging clearly as such, is whether the timing of that ejection had any relationship to the orbital phase of the proposed companion. The surface mass ejection of 2019 occurred during a period that some researchers have noted is consistent with a particular phase of the 6-year-long secondary period cycle. The potential connection is not proven. Correlation is not causation, especially in a star whose surface activity is driven by multiple overlapping processes. But the theoretical pathway for such a connection is not unreasonable. If Siwara's orbital passage at certain phases brings it through regions of the envelope where gas density is slightly higher, the localized energy injection at those orbital positions could, in principle, produce pressure fluctuations that propagate inward or outward and influence the conditions for surface ejection events. The orbital interaction might act as a trigger, or more accurately as a biasing factor, making certain types of surface events slightly more likely at certain orbital phases. The great dimming, whatever connection it may or may not have to the binary dynamics, matters primarily for a different reason in this context. It showed that the system is capable of dramatic surface behavior, that the envelope of Betelgeuse is responsive to disturbances from within, and that even events we initially classify as purely internal can have origins or amplifying factors that we have not yet fully accounted for. It is a reminder that a star being stirred from the inside might express that disturbance in ways that look, on the surface, like something else entirely. Part 13. The Final Descent. Let us follow Siwara forward in time, not across human generations, but across the long arc of orbital mechanics, carrying the trajectory of what is already happening to its logical conclusion. Currently, the orbit sits at approximately 4 astronomical units from the centre of Betelgeuse. That is a meaningful distance. It places Siwara in a region of the stellar atmosphere that is still genuinely diffuse, where the drag is real but manageable on short timescales, and where the orbital period of roughly 6 years is long enough for the energy loss per orbit to accumulate gradually rather than catastrophically. The system is not in its final seconds, it is in its final chapters, but the inspiral is not linear. This is the part that matters most for understanding what the future looks like. In a linear decay, you would lose the same amount of orbital energy per orbit regardless of where in the inspiral you are. The total timescale would be long but predictable. The actual inspiral is exponential in its acceleration. As the orbit shrinks and gas density increases, each subsequent orbit loses more energy than the last. The rate of orbital decay speeds up. The companion descends faster and faster as it gets deeper into the star. Think of it in terms of depth and resistance. In the outermost regions of Betelgeuse's envelope, the gas is so thin that Siwara can complete thousands of orbits while losing only a tiny fraction of its total orbital energy. But as it descends into progressively denser layers, each orbit becomes more costly in energy terms. There is a transition point, somewhere in the intermediate layers of the star, where the energy loss per orbit becomes so large that the inspiral accelerates dramatically. Below that transition point, the descent to the core happens on a much shorter timescale than the earlier, slower phase. We are probably still in the earlier, slower phase. The estimate of 9,000 to 10,000 years for the merger. Timescale reflects the total remaining time in the current regime. But built into that estimate is the knowledge that the final stages of the descent will be far more rapid than the average rate implies. The last few thousand years before the merger may see the orbital decay accelerating to a point where what was a gradual, almost geological process becomes something far more dynamic. The core of Betelgeuse, where the nuclear burning is occurring, is a very different environment from the tenuous outer atmosphere. It is dense, hot, and structurally rigid in comparison to the surrounding envelope. When Siwara approaches the boundary of that core region, the interaction changes qualitatively. The drag is no longer just atmospheric friction. The forces become extreme, and the outcome is not a gentle arrival, but something closer to a collision in slow motion. The descent is already decided. The only question is what happens at the bottom. Part 14. The moment of impact. When Siwaha reaches the boundary of Betelgeuse's dense interior, after thousands of years of spiralling through progressively thicker gas, the accumulated energy of that entire journey becomes suddenly, catastrophically relevant. The merger itself, the moment when two stellar cores interact at the kind of proximity that makes separation impossible, is not a quiet event. The energy scales involved are staggering. Siwaha's orbital energy at the moment of final merger, combined with the gravitational potential energy released during the final descent, will be released into the surrounding stellar material in a time window that is extremely short compared to the centuries of slow in-spiral that preceded it. The result is an explosive energy injection into the envelope of Betelgeuse on a scale that dwarfs anything that has happened during the slow in-spiral phase. There is a class of astronomical events called luminous red novae, or merger novae, that astronomers believe are caused by exactly this kind of stellar merger. When two stars finally collide after a period of common envelope inspiral, the energy release can produce a transient brightening that, in some observed cases, has been bright enough to temporarily rival the luminosity of small galaxies. The canonical example is a system called V1008 Scorpii, which brightened dramatically in 2008 and is now understood to be a post-merger remnant. Another is a contact binary called KIC 9832227, which astronomers predicted in 2022 would merge within the following few years based on an observed decreasing orbital period, a real-time prediction for a real-time event. For Betelgeuse, the merger nova scenario carries an additional layer of complexity. This is not a merger between two ordinary stars in empty space. This is a merger inside a massive red supergiant that is already approaching the end of its nuclear fuel supply. The energy released by the merger could be deposited into an envelope that is already structurally stressed by decades of accelerating turbulence, already losing mass at an elevated rate, already containing asymmetric density structures shaped by the in-spiral. The response of the envelope to that sudden energy injection is not something that can be precisely predicted with current models. One possibility is that the merger energy triggers a shockwave powerful enough to initiate core collapse, effectively compressing the final step of Betelgeuse's stellar evolution by potentially hundreds of thousands of years, not causing a supernova on its own, but pushing a core that was already close to instability over the threshold. Betelgeuse, based on its current state, was expected to undergo core collapse on a timescale of somewhere between 100,000 and a few 100,000 years from now. The merger event could dramatically shorten that window. If it does, what would we see from Earth? Betelgeuse is close enough that a supernova would be extraordinary. Estimates suggest it would reach an apparent magnitude of somewhere around -12, which is about as bright as the full moon, visible in daylight, casting shadows at night, a beacon in Orion for weeks to months before fading. No one alive today will see it, but the physics determining what it will look like is being written right now by Siwaha's descent through the atmosphere above. Part 15. 3 Endgames. The future of the Betelgeuse system does not have a single determined outcome beyond the certainty of the merger itself. The merger will happen. The physics of common envelope evolution makes that inevitable. But what the merger produces, what comes after the two stellar cores finally interact, depends on variables that current models cannot precisely constrain. And that uncertainty is not a failure of the science. It is the science being honest about a system that has never been observed at this proximity before. So let us walk through the 3 scenarios that researchers currently consider plausible. Not as speculation, but as distinct physical pathways, each one grounded in real mechanics, each one leading to a dramatically different version of how this story ends. The first scenario is the one that gets the most attention, and for good reason. In this outcome, the merger event triggers the core collapse of Betelgeuse prematurely, initiating a supernova explosion before the star would have naturally reached that endpoint, through nuclear fuel exhaustion alone. Here is what that means in practical terms. Betelgeuse, left entirely to its own nuclear clock, probably has somewhere between 100,000 and several 100,000 years of fuel burning left before its iron core grows massive enough to collapse under its own gravity. That is the standard endpoint for a star of its mass, the inevitable gravitational implosion that produces a supernova. Under normal circumstances, you would simply wait for the fuel to run out. But the merger does not wait for the fuel. When Siwara finally reaches the core region of Betelgeuse after its long spiral through the envelope, the energy deposited into the stellar interior in the final stages of that descent is not a gentle addition. It is a sudden, violent injection of energy into an already stressed system. The core of Betelgeuse, at that point in its evolution, will be composed of progressively heavier nuclear burning shells, each one closer to the iron endpoint that triggers collapse. The merger energy pushes that already stressed interior over the instability threshold, and the collapse proceeds rapidly. Not in thousands of years, rapidly. The result is a core collapse supernova, but not a standard one. Because remember what Siwara's inspiral has been doing to the surrounding atmosphere for thousands of years before that final moment. It has been driving enhanced mass loss, asymmetric outflows, pre-ejected shells of circumstellar material distributed in a non-spherical pattern around the star, shaped by the orbital dynamics of the inspiral itself. When the supernova shockwave expands outward from the collapsing core, it does not travel through empty space. It travels through that pre-structured material. The interaction between the blast wave and those circumstellar shells can make the explosion brighter, longer lasting, and more asymmetric than a standard core collapse in a clean environment. This is the dramatic outcome. The one where binary interaction determines not just the character of the explosion, but its timing. The one where Siwara's long fall ends up pulling the trigger on one of the most energetic events our galactic neighbourhood will ever produce. The second scenario is more subdued in its immediate drama, but in some ways more scientifically fascinating. In this version, the merger completes without immediately triggering core collapse. The two stellar cores interact, the orbital energy is fully deposited into the surrounding material, and rather than pushing the system over the collapse threshold, the energy is absorbed and redistributed throughout the stellar interior. The combined system then settles into a new structural configuration. Betelgeuse continues its evolution, but now as a fundamentally different star from the one that existed before the merger. Think about what that means. Siwara contributes roughly 1.5 solar masses of additional material to the system. That additional mass alters the gravitational pressure on the core, changes the timescale and progression of the remaining nuclear burning stages, and potentially restructures the internal composition profile in ways that a standard single-star model would never predict. The star that eventually reaches core collapse in this scenario is not the same Betelgeuse we're observing today. It is a merged object, carrying the combined nuclear history of two different stars that spent thousands of years interacting inside a shared envelope. And here is the quietly remarkable implication of that. The supernova that eventually results from this merged star would carry the fingerprints of that merger in its observable characteristics. The light curve, the way the brightness evolves over time after the explosion, the spectral composition of the ejector, the specific elements present and their distribution, the geometry of the expanding remnant. All of these would reflect the unusual interior structure of a merged star rather than a standard single stellar evolution. Future astronomers, observing that supernova remnant with instruments we have not built yet, would in principle be able to decode that history from the explosion's character. The merger would be preserved in the ashes. The third scenario is the most computationally difficult to model, and the one about which the least can currently be said with any confidence. In this version, Betelgeuse reaches its natural core collapse threshold before the merger completes. The nuclear clock runs out before the orbital clock does. Siwara, still orbiting somewhere inside the envelope, has not yet reached the core when Betelgeuse spontaneously undergoes gravitational collapse and explodes. What happens to a star that is embedded inside another star when that star explodes around it is a genuinely open question. The expanding blast wave from the core collapse would interact with Siwaha as a physical obstacle, a stellar mass object sitting inside the explosion's propagation path. Several outcomes are theoretically possible. The companion could be expelled violently outward by the blast wave, becoming a runaway star moving at high velocity through the galaxy. It could be partially or fully incorporated into the collapsing remnant, adding mass to whatever neutron star or black hole forms at the centre. It could disrupt the symmetry of the expanding shock wave in ways that produce observable asymmetries in the supernova remnant. Or some combination of these effects could occur simultaneously in different regions of the interacting system. The three-dimensional hydrodynamic simulations required to model this scenario accurately demand computational resources that push the current limits of what is possible, and the results that do exist carry large uncertainties. What all three scenarios share, regardless of which one ultimately describes the real fate of Betelgeuse, is that binary interaction fundamentally rewrites the story. The explosion of Betelgeuse, whenever it arrives, and whatever form it takes, will not be the explosion of a lonely dying star following a standard textbook evolutionary path. It will be the explosion of a system with a hidden history, a system shaped by thousands of years of internal inspiral atmospheric disturbance, asymmetric mass loss, and the gradual, irreversible descent of one star through the body of another. The three-dimensional simulations published by Scheiber and collaborators in 2024 suggest that the first scenario, the premature triggered collapse, is plausible under current parameter estimates for the Siwaha in spiral. But the uncertainties in those parameters are large enough that the other two scenarios cannot be dismissed. The honest answer is that we do not yet know which path this system will take. What we do know is that whichever path it takes, the inspiral is the reason. Siwaha's fall through Betelgeuse's atmosphere is not background detail. It is the central mechanism determining everything that follows. The outcome is uncertain. The inspiral is not. And the inspiral has already decided that none of these three endings look anything like the lonely death of a single star burning out in silence. Something more complicated, more violent, and more consequential is coming. The only question left is exactly which version of it we're watching build toward. Part 16. The Timeline Paradox. There is an interesting tension at the centre of the Betelgeuse story that does not resolve neatly, and it is worth sitting with that tension for a moment rather than papering over it, because this is the part where the science gets genuinely uncomfortable in the best possible way. Not uncertain because we lack data. Uncertain because two completely separate physical processes are governing the fate of the same star, operating on timescales so different from each other that reconciling them into a single coherent prediction has so far defeated every attempt to do so. To understand why that matters, we need to go back to what the standard picture of Betelgeuse looked like before the binary hypothesis entered the conversation. For most of the last several decades, the question of when Betelgeuse would explode was treated as a problem with a relatively well-defined answer, even if the error bars were wide. Astronomers would look at the star's current surface temperature, its luminosity, the inferred state of its nuclear burning based on where it sits on evolutionary tracks derived from stellar models, and they would triangulate a position on the map of stellar aging. Betelgeuse, by those measurements, was clearly old, clearly in the late stages of its life, clearly burning through the heavier nuclear fuels that come after hydrogen and helium are exhausted. But most estimates place the actual supernova somewhere between 100,000 and 1 million years from now. Some analyses pushed shorter, some ran longer, but the general consensus was stable. Approaching the end, yes. At the doorstep, no. Not on any timescale that should keep anyone awake at night. That consensus was uncomfortable enough to be interesting, but not dramatic enough to be alarming. Betelgeuse was a dying star in the way that a candle is dying from the moment it is lit. Technically true, practically irrelevant on human timescales. Then the long secondary period analysis complicated everything. and it did so in two directions simultaneously, which is what makes this genuinely paradoxical rather than simply uncertain. The first complication runs in the direction you might not expect. The 6-year-long secondary period, that repeating brightness cycle that had been sitting in Betelgeuse's light curve for over a century, was not just an unexplained curiosity. It was being actively used by some researchers as an observational input for modelling the star's internal structure. If a star pulses with a certain period, that period encodes information about the physical conditions inside the star, the density profile, the pressure gradients, the relationship between different internal layers. So the long secondary period was being fed into stellar interior models as a structural constraint, helping to pin down parameters that are otherwise difficult to measure directly. If the long secondary period is actually an orbital signature, the footprint of Siwaha's orbit rather than an internal stellar oscillation, then every model that used it as a structural constraint was built on a misidentified input. The foundation is wrong. And when researchers go back and rebuild those models without the long secondary period as a structural parameter, something unexpected happens. Some estimates for the remaining nuclear burning lifetime of Betelgeuse actually increase, slightly but measurably. The star, considered purely as an isolated nuclear burning object without the binary complication, might have more time on its internal clock than the pre-binary model suggested. Let that sit for a moment. The discovery of a companion that is spiralling inward toward an inevitable merger, a companion whose existence implies a dramatic and potentially premature end for the system, simultaneously suggests that the star's own nuclear fuel supply might last a little longer than we thought. The binary hypothesis makes the long-term future look both more stable and more violent at the same time, depending on which process you're following. And that brings us to the second complication, which runs in the opposite direction with considerably more urgency. The inspiral of Siwaha through Betelgeuse's atmosphere operates on its own timeline, not a nuclear timeline, not a fuel-burning timeline, an orbital mechanics timeline. The rate at which Siwaha loses orbital energy and descends through progressively denser layers of the stellar atmosphere is governed by the density profile of that atmosphere and the mass of the companion. It does not care how much hydrogen or helium or carbon is left in the core. It does not respond to the nuclear burning state of the star at all. It is a purely mechanical process, driven by drag and gravity, and it runs on a timescale of approximately 9,000 to 10,000 years from the current orbital position to the merger completion. 9,000 to 10,000 years is a long time by any human measure. Civilizations rise and fall in centuries. The entirety of recorded human history fits inside about 5,000 years. 10,000 years is twice that. But against the nuclear timeline of hundreds of thousands of years, it is nothing. It is less than 5% of the remaining nuclear burning lifetime. It is a rounding error on a stellar timescale. And if the merger, when it completes, deposits enough energy into the core region to trigger premature gravitational collapse, then the nuclear clock stops mattering entirely. The inspiral clock overrides it. Siwaha's orbital mechanics, not Betelgeuse's fuel supply, determines when the explosion happens. The hundreds of thousands of years remaining on the nuclear clock become irrelevant the moment the merger pushes the core over the instability threshold. This is what makes the timeline paradox genuine rather than just a semantic confusion about large numbers. Two dominant physical processes are governing the fate of the same object. One of them, the nuclear evolution, is the process that stellar physicists have been modelling for decades, with sophisticated codes, extensive observational calibration, and a deep theoretical foundation. The other, the orbital inspiral, is a process that is far less well characterized observationally, governed by fluid dynamics inside a stellar atmosphere that no simulation has yet captured with full accuracy, and operating on a timescale that is an order of magnitude shorter than the nuclear one. The researchers studying Betelgeuse's nuclear evolution and the researchers studying Betelgeuse's orbital dynamics are, in a very real sense, working on different stars. One group is modelling a single red supergiant burning through its late nuclear stages. The other is modelling a common envelope binary in mid-inspiral. Both models are internally consistent, both are grounded in real physics, but they produce predictions for the future of Betelgeuse that are not yet reconciled into a single unified framework, and the process of reconciling them requires understanding the interaction between nuclear evolution and orbital dynamics at a level of detail that current models have not achieved. Consider what a unified model would actually need to do. It would need to track the orbital decay of Siwaha through a stellar atmosphere whose density profile is itself evolving as the nuclear burning progresses. As Betelgeuse ages, its internal structure changes, which changes the density gradient of the envelope, which changes the drag force on Siwaha, which changes the inspiral rate. The two clocks are not independent, they are coupled. The nuclear evolution affects the orbital decay rate, and the orbital energy injection from the inspiral affects the thermal structure of the envelope, which in turn feeds back into the stellar evolution. Building a model that captures all of those couplings simultaneously, across timescales ranging from years to hundreds of thousands of years, is a computational and theoretical challenge that the field is actively working toward but has not yet solved. What we are left with for now is the honest acknowledgement that Betelgeuse has two timelines running simultaneously, and the relationship between them is unresolved. The nuclear clock suggests patience, the inspiral clock suggests urgency, and the question of which one actually determines the ending, whether Betelgeuse dies on its own fuel schedule or whether Siwaha's descent pulls the trigger first, is one of the most important open questions in stellar astrophysics right now. The inspiral clock is ticking faster. It has been ticking faster with every orbit Siwaha completes, and the uncertainty that creates is not a failure of the model or a gap in the data. It is the model doing its job correctly, faithfully representing a system that genuinely has more than one way to end, driven by more than one physical process, on more than one time scale. The universe, as it turns out, did not consult the standard textbook before deciding how to arrange this particular star, and the fact that we're only now beginning to read both clocks at the same time is either a humbling reminder of how much we missed, or an exciting indication of how much we are still learning. Probably both. Part 17. The 2027 Observation Window. Every orbital system has a geometry. That sounds like an abstract statement, but what it means in practice is surprisingly concrete. From where we sit on Earth, a companion object orbiting inside the atmosphere of Betelgeuse does not always present itself at the same apparent position relative to the star's centre. The orbit is inclined at some angle to our line of sight, and as Siwaha moves through that orbit over its roughly 6-year period, there are moments when it passes behind the bright disk of the star from our perspective, moments when it passes in front, and moments when it reaches its maximum apparent sideways displacement from the centre. That last configuration, the one where the geometry gives us the best possible angular separation between the companion and the overwhelming glare of the primary star, is called the maximum elongation, and the next one is coming. Based on the current orbital models derived from the long secondary period analysis and the wobble measurements, the predicted maximum elongation of Siwaha occurs in approximately 2027. That is not a distant date on an astronomical calendar. It is within the operational lifetime of instruments that are already built, already pointed at the sky, and in some cases already accumulating data on Betelgeuse right now. The astronomy community is aware of this window. They are planning for it. And the level of coordinated observational effort being directed toward this event reflects how seriously the field is taking the binary hypothesis, and how much a precise measurement at that moment could change the conversation. To understand why 2027 matters so much, it helps to appreciate how difficult the detection problem actually is. Betelgeuse is an extraordinarily bright star. Its surface luminosity is so overwhelming that any companion object embedded within or near its atmosphere is essentially trying to be seen while standing next to a searchlight. The contrast ratio between the primary star and a companion of Siwaha's estimated brightness buried inside the stellar envelope is enormous. At most orbital phases, trying to detect Siwaha directly against the disk of Betelgeuse is like trying to spot a candle flame inside a spotlight from across a city. The maximum elongation does not eliminate that contrast problem, but it shifts the geometry in our favour. Instead of looking for a faint signal projected against the brightest background available, we are looking for it at maximum angular distance from that background, where the overwhelming contribution of the primary star falls off enough to give a companion signal its best possible chance of emerging above the noise. The detection attempt made with the Gemini North Telescope using speckle interferometry in 2025 already exploited a version of this geometric advantage, producing a faint secondary signal near the predicted orbital position at a statistical significance of approximately 1.5 sigma. That result sits below the threshold that the scientific community considers a confident detection, but it is precisely consistent with where the orbital model said the companion should be. Think of it as a preliminary sighting through fog. You cannot confirm the shape, but something is there in the right place, and the fog is about to thin. The instruments that could be brought to bear during the 2027 window represent some of the most powerful optical and infrared observing capabilities currently available to humanity. The Very Large Telescope Interferometer, operated by the European Southern Observatory in the Atacama Desert of Chile, is perhaps the most relevant. This facility does not function as a single telescope in the traditional sense. It combines the light collected by 4 large unit telescopes, each with an 8.2 meter primary mirror, along with several smaller auxiliary telescopes, using a technique called interferometry to synthesize an effective aperture far larger than any single instrument could achieve. The angular resolution available to the VLTI at certain wavelengths is sufficient to resolve features on the surface of Betelgeuse itself, which is an extraordinary statement about a star 650 light-years away. Applying that resolution to the search for a companion signal at maximum elongation, with optimized instrument configurations targeted specifically at the predicted position, gives the 2027 campaign its best ground-based tool. Adaptive optic systems on other large ground-based facilities contribute additional capability. The fundamental problem with observing through Earth's atmosphere is turbulence. Air moves, temperature gradients create refractive variations, and the wavefront of light arriving from a distant source gets scrambled on its way down through the atmospheric column. The result is the familiar twinkling of stars, which is aesthetically pleasant and scientifically catastrophic if you are trying to achieve the theoretical resolution limit of a large telescope. Adaptive optic systems correct for this in real time by measuring the distortion of the incoming wavefront using a reference source, typically a bright star or an artificial laser guide star, and then applying compensating corrections to a deformable mirror hundreds of times per second. When these systems work well, they can restore image quality close to the diffraction limit of the telescope, which for an 8-meter class instrument at visible wavelengths corresponds to angular scales small enough to be genuinely useful for the Betelgeuse companion search. The James Webb Space Telescope adds a different dimension to the campaign. Operating above the atmosphere entirely, Webb does not struggle with turbulence at all. Its mirror, 6.5 meters in diameter, delivers its full theoretical resolution at the infrared wavelengths it is optimized for. An infrared is a particularly interesting regime for this search because the contrast ratio between a stellar companion and the surrounding stellar atmosphere changes with wavelength. At visible wavelengths, Betelgeuse dominates overwhelmingly. At certain infrared wavelengths, the emission from the cooler outer atmosphere drops relative to what a companion object of Siwaha's estimated temperature would produce, potentially improving the contrast enough to make a detection more tractable. Webb has already been used to study the circumstellar environment of Betelgeuse in exquisite detail. Targeting it specifically at the predicted companion position during the maximum elongation window is a natural and powerful application of its capabilities. But here is the thing about what astronomers are actually hoping to achieve in 2027, and it goes significantly beyond simply confirming that Siwaha exists. The most scientifically valuable measurement would not be a single detection at one epoch. It would be a positional measurement that can be compared to earlier positional measurements to directly track the orbital motion over time. The inspiral hypothesis does not just predict that a companion exists at a certain location, it predicts a specific trajectory. A decaying orbit moves differently from a stable one. In a stable circular orbit, the companion returns to exactly the same position after exactly one orbital period, every time, indefinitely. In a decaying orbit, the companion returns to a slightly different position after each period, displaced inward from where it was the previous time, with the displacement growing progressively larger as the decay accelerates. If you can measure the position of Siwaha at two separated epochs, and if those positions are consistent with the arc of a decaying orbit rather than a stable one, you have done something that no amount of indirect evidence can fully replicate. You have directly observed the inspiral in progress, not inferred it from brightness variations, not modelled it from atmospheric disturbances, measured it as a positional change in a stellar companion over a defined time interval. That measurement would transform the status of the binary hypothesis from a well-supported working model into a confirmed physical reality with a directly calibrated decay rate. And a calibrated decay rate feeds back into everything else. It constrains the atmospheric density profile of Betelgeuse at Siwara's orbital radius. It pins down the drag coefficient in ways that improve the hydrodynamic simulations. It sharpens the inspiral timescale estimate from a range of several thousand years to something considerably more precise. And it provides the first direct empirical anchor for models of common envelope evolution in any system anywhere, not just Betelgeuse. The 2027 window is not guaranteed to deliver all of this. The angular separation at maximum elongation will still be small by the standards of most optical instruments. The contrast challenge will still be formidable. Weather, scheduling, instrumental availability, and the always present possibility that the companion signal simply falls below detection thresholds, even under optimal conditions, all introduce real risk of a null result or an ambiguous one. But even a null result would be informative. If the predicted companion position shows nothing, even with the best available instruments under optimal geometry, that outcome places constraints on the companion's brightness, and therefore on its nature. It does not immediately falsify the binary hypothesis, because there are plausible configurations in which the companion is fainter than current estimates, or embedded more deeply in the envelope than the models assume. But it would force a revision of those models and redirect the search strategy. The 2027 window is, in short, the moment when the Betelgeuse binary hypothesis gets its most serious direct test. The difference between what the data currently supports and what the observation could confirm is the difference between a very compelling case and a verified discovery. And verified discoveries in astrophysics are the ones that change textbooks. The instruments are ready, the orbital geometry is converging, and the question that has been building across more than a century of misread signals is about to get its clearest shot at an answer. Part 18. What if this isn't unique? Here is a thought that follows naturally from everything we have discussed, and it is one that several researchers have begun to take seriously. If a companion star could spiral inside Betelgeuse for thousands of years, leaving an orbital signature in the brightness record that was visible for over a century but consistently misidentified as something else, how many other stars in the galaxy are doing the same thing right now? How many stellar systems are we currently looking at, measuring, modelling, and filing away under confident labels, while a hidden companion spirals silently through the envelope, waiting to be correctly interpreted? That question is not rhetorical. It has a potential answer, and the answer is uncomfortable in the best possible scientific way. The long secondary period is not a quirk unique to Betelgeuse. It is a feature that shows up across a significant fraction of evolved massive stars, specifically the class of objects known as red supergiants and asymptotic giant branch stars. These are stars in the late stages of their lives, stars that have exhausted their core hydrogen, expanded to enormous sizes, and entered the final chapters of their nuclear evolution. They are the population of objects from which supernovae eventually emerge. They are, in other words, exactly the stars whose evolutionary endpoints matter most for our understanding of how massive stars die and what they leave behind. Studies of stellar catalogues compiled from long baseline photometric surveys have found long secondary periods distributed across this population with a regularity that is difficult to ignore. The periods range from roughly 2 years at the short end to approximately 10 years at the long end, clustering in a range that overlaps almost precisely with the orbital timescales you would expect from a companion embedded in the extended atmosphere of a red supergiant at the kind of orbital separations where common envelope evolution would place it. Not every star in the catalogue shows a long secondary period, but a substantial fraction do, enough that if each one represents a hidden companion rather than an internal stellar process, the population of active common envelope systems in our galaxy would be considerably larger than current models assume. The debate about the origin of long secondary periods in these other systems mirrors the debate that played out for Betelgeuse, just with less data and less attention. Pulsation has been proposed and found wanting for the same reasons it fails for Betelgeuse. The structural changes required to drive a multi-year pulsation are inconsistent with what stellar interior models predict for stars of these masses and radii. Convection has been invoked and faces the same fundamental objection that convection is stochastic rather than periodic. Magnetic cycles have been suggested and run into the same observational obstacles, and the orbital interpretation, the one that fits the physics most cleanly, has been noted in the literature for individual systems without ever being systematically pursued as the primary explanation for the population as a whole. The reason that systematic pursuit has not happened yet is partly sociological and partly technical. Sociologically, the single-star evolutionary framework for massive stars is deeply embedded in the field. It is the foundation on which stellar population synthesis models are built, on which supernova rate predictions are calibrated, on which the expected distributions of neutron stars and black holes across the galaxy are calculated. Proposing that a significant fraction of the evolved massive star population is actually in active common envelope systems, rather than proceeding through standard single-star evolution, is not a small amendment to the existing framework. It is a challenge to one of its core assumptions. Challenges of that magnitude require correspondingly strong evidence before they gain broad traction, and the evidence, while building, has not yet reached the threshold that would force a wholesale revision. Technically, the challenge is even more daunting. Betelgeuse is the closest red supergiant to Earth. At 650 light-years, it is close enough that its disk can be partially resolved, that its surface features can be imaged with interferometric techniques, that the atmospheric velocity structure can be mapped in reasonable detail, and that a companion signal at a few astronomical units separation might, under optimal conditions, be detectable at the level of 1.5 sigma with current instrumentation. That is already at the edge of what is possible. Now consider that the next nearest red supergiants are considerably farther away. A star 5 times more distant than Betelgeuse, at roughly 3,000 light-years, would require angular resolution 25 times finer than what is needed to detect Suara. That is not a modest scaling challenge. That is the difference between something that strains current technology and something that exceeds it by a large margin. Direct imaging of embedded companions in more distant red supergiant systems is not currently feasible with any existing or near-term planned facility. But direct imaging is not the only tool available, and this is where the Betelgeuse case becomes genuinely instructive for how to approach the broader population. The evidence that built the binary hypothesis for Betelgeuse was assembled almost entirely from indirect methods. The long secondary period extracted from photometric light curves, the stellar wobble detected from astrometric position measurements, the atmospheric velocity asymmetries mapped from spectroscopic data, the circumstellar asymmetries documented from interferometric imaging of the immediate environment rather than the companion itself. None of these techniques required resolving the companion directly. They all worked by detecting the companion's influence on the primary star and its surrounding material. Those same techniques can be applied to other red supergiant systems. Light curves spanning decades are available for large samples of evolved massive stars from surveys like the American Association of Variable Star Observers database, from the All-Sky Automated Survey, and from the increasingly comprehensive photometric archives being assembled by modern sky survey programs. Systematic periodicity analysis of those archives, specifically searching for the combination of a primary pulsation period and a longer secondary period with the strict regularity that would distinguish an orbital signature from convective noise, could identify a candidate population of hidden binary systems without requiring any new observations at all. The data already exists. It is a question of applying the right analytical framework to it. Wobble detection from astrometric measurements becomes more feasible as the precision of space-based astrometry improves. The Gaia mission, the European Space Agency's ongoing program to measure the positions and motions of over 1 billion stars with extraordinary precision, has accumulated a multi-year baseline of positional measurements for a large fraction of the bright star catalogue. Mining that dataset for the kind of periodic positional wobble that would indicate a companion in an evolved star's envelope is a computationally intensive but technically tractable project. It would not provide the angular resolution needed to detect a companion directly, but it could flag systems showing the astrometric signature of an embedded massive companion, directing follow-up resources toward the most promising candidates. Spectroscopic surveys that measure atmospheric velocity structures in red supergiants have been conducted for various scientific purposes over the years, and many of the resulting datasets have not been specifically analysed for the kind of phase-correlated asymmetric velocity patterns that the Hubble ultraviolet data revealed in Betelgeuse. Reanalysing those existing spectroscopic archives with the binary hypothesis explicitly in mind could extract additional candidates from data that was collected for entirely different purposes. The cumulative picture that emerges from all of this is one where Betelgeuse is not the eccentric outlier of stellar astronomy, but rather the nearest, best resolved, and most thoroughly characterized member of a population that may be surprisingly large. The galaxy contains on the order of several hundred known red supergiant stars within a few thousand light-years. If even a modest fraction of those systems carry hidden companions in active common envelope in spiral, the implications for how we model the final stages of massive stellar evolution are profound. Every supernova model currently in use was built on the assumption that the stars producing those explosions arrived at the endpoint of their evolution as single objects, shaped only by their own internal physics and their interactions with stellar winds and the surrounding interstellar medium. If binary interaction during the common envelope phase is instead a standard feature of the final evolutionary stages for a significant fraction of massive stars, then the diversity of supernova characteristics we observe, the range of explosion energies, the variety of remnant types, the unexpected luminosities that have occasionally defied single-star models, may be partly a reflection of hidden binary histories that we have not been accounting for. Betelgeuse, in this reading, is the key that unlocks a different way of looking at an entire class of objects. Not an extraordinary exception demanding its own special explanation, but the nearest and most legible example of something the galaxy has been doing all along, in system after system, at distances too great for our current instruments to resolve directly, with signals we have been measuring for decades without correctly understanding what they were telling us. The long secondary periods are there in the catalogues. They have been there for years, and if the Betelgeuse analysis holds, they have been trying to tell us something the whole time. Part 19. The Cannibal Star Hypothesis. There is one more layer to this story that deserves more than a passing acknowledgement, because it does something that the rest of the evidence does not quite do on its own. It extends the history of Betelgeuse backward. Not forward into the merger and the explosion and the eventual remnant, but backward into the deep past of a star that has existed for somewhere between 8 and 10 million years, and asks a question that changes the entire character of what we are looking at. what if Siwaha is not the first? To understand why that question arises, we need to return to the rotation anomaly, because it is the piece of evidence that refuses to be fully accounted for by the current in spiral alone. Betelgeuse is rotating at approximately 5 km per second at its equator. Some measurements push that figure toward 10 or even 15 km per second, though the higher end of that range carries significant uncertainty due to the convective contamination problem discussed earlier. Even accepting the conservative lower estimate of 5 km per second, that number is roughly 5 times higher than theoretical models predict for a red supergiant of Betelgeuse's age and mass evolving in isolation. The physics of stellar spin-down during the expansion from a main sequence star to a red supergiant is well understood, and it is unambiguous in its prediction. A star expanding to hundreds of times its original radius should be rotating extremely slowly by the time it reaches Betelgeuse's current evolutionary state. The angular momentum is still there, conserved in the total system, but it should be spread across such an enormous volume of stellar material that the surface rotation rate drops to a tiny fraction of its original value. The inspiral of Siwaha provides a partial explanation. As Siwaha orbits through the envelope, it drags gas with it, transferring orbital angular momentum into the surrounding stellar material. That transfer is real, it is physically expected, and it contributes to spinning up the outer layers of Betelgeuse in the direction of the orbit. But here is the problem. When researchers attempt to calculate how much angular momentum Siwaha's current orbit could have deposited into Betelgeuse's envelope over the inspiral period, the numbers fall short of accounting for the full observed rotation, particularly at the higher end of the measurement range. The current in spiral, taken alone, does not fully close the angular momentum budget. There are 2 ways to interpret that shortfall. The first is that the high-end rotation measurements are substantially inflated by convective mimicry, that the actual rotation rate is close to the low end of the observed range, and that the current in spiral is sufficient to explain it. This is a legitimate possibility and cannot be ruled out with current instrumentation. The second interpretation is that Siwaha is not the only source of angular momentum that has been deposited into Betelgeuse over its lifetime, that something else, something earlier, contributed rotational energy that is still present in the star's spin today. That second interpretation is the foundation of what researchers informally call the cannibal star hypothesis. The idea is straightforward in its basic form, even if its implications are anything but. Betelgeuse, across its 8 to 10 million years of existence, may have consumed a companion star before Siwaha ever began its current in spiral. A prior binary companion, orbiting at some distance during an earlier phase of Betelgeuse's evolution, could have been engulfed as the primary star expanded, undergone its own common envelope in spiral, and merged with the core region of Betelgeuse at some point in the past. That merger would have deposited angular momentum into the stellar system in a quantity potentially large enough to explain the elevated rotation rate we observe today, even accounting for the subsequent spin-down that would have occurred during Betelgeuse's continued expansion since the merger. The prior merger would also have left other signatures. A merger event deposits not just angular momentum but chemical species into the stellar interior. If a companion of a certain mass and evolutionary state merged with Betelgeuse at some point in its past, the resulting chemical mixing would alter the composition profile of the stellar interior in ways that could potentially be detected through detailed spectroscopic analysis of Betelgeuse's surface abundances. Some researchers have noted that certain aspects of Betelgeuse's observed surface chemistry and the peculiarities in stellar interior models fitted to its observed properties are not fully reproduced by standard single-star evolutionary tracks. The models work reasonably well in broad strokes, but the detailed fits show residuals, discrepancies between prediction and observation that single-star models struggle to eliminate entirely. These residuals are not dramatic. They are not the kind of obvious contradiction that forces an immediate revision of the model. They are subtle enough that they could plausibly be explained by uncertainties in the input physics of the stellar models themselves, by uncertainties in the measured surface parameters of Betelgeuse, or by the genuine complexity of modelling a star with large convective cells and significant mass loss. But they are also the kind of subtle discrepancies that a prior merger event might naturally produce, and the fact that the rotation anomaly points in the same direction gives the combined circumstantial case a coherence that is worth taking seriously even in the absence of direct confirmation. Consider what the timeline of such a scenario might look like. Betelgeuse forms from a molecular cloud collapse somewhere between 8 and 10 million years ago, possibly as part of a multiple star system. In stellar terms, massive stars rarely form truly alone. The environments that produce stars massive enough to become red supergiants tend to produce them in clusters and associations, often with nearby companions at a range of separations. During Betelgeuse's main sequence phase, when it was a hot, luminous blue star burning hydrogen in its core, a companion at moderate orbital separation would have been entirely stable and unremarkable. As Betelgeuse evolved off the main sequence and began its expansion toward the red supergiant phase, its growing radius would have started to encroach on the orbital space of nearby companions. At some point, perhaps several million years ago, a companion at sufficiently close orbital separation would have been engulfed as the expanding envelope reached its orbit. That engulfment would have initiated a common envelope phase. The companion would have spiraled inward, depositing orbital energy and angular momentum into the envelope, and eventually merged with the core or the dense interior layers of the still evolving primary. The energy from that merger would have temporarily altered the structure and luminosity of Betelgeuse, perhaps producing a luminous red nova event that would have been visible across large distances if any observers had been present to see it. After the merger, Betelgeuse would have continued its evolution, now carrying the angular momentum legacy of that consumed companion embedded in its rotation profile. Millions of years later, in the current epoch, Betelgeuse has expanded to its present enormous size, and a second companion, Siwaha, finds itself at an orbital separation that places it inside the extended atmosphere. Whether Siwaha was always a companion to Betelgeuse, orbiting at a distance that only became problematic when the star expanded far enough to engulf it, or whether it was captured gravitationally at some point during Betelgeuse's evolution, is an open question. But here it is, orbiting at approximately 4 astronomical units, falling inward, depositing its own angular momentum contribution on top of whatever the prior merger left behind. Under this reading, Betelgeuse is not a star approaching its first experience of binary interaction. It is a serial participant in common envelope evolution, a star that has already consumed at least one companion and is in the process of consuming another. Its current state, its anomalous rotation, its unusual internal structure, its elevated mass loss, its atmospheric turbulence, reflects not the evolution of a single isolated object, but the accumulated legacy of multiple stellar interactions across millions of years. The star we see in Orion tonight is the product of a history that involved other stars, other orbits, other mergers, and other energy depositions that have shaped everything from its spin rate to its chemical composition to the density profile of the atmosphere that Siwaha is currently falling through. This is speculative. It needs to be said clearly and without apology. There is no direct observational evidence for a prior merger in the form of a confirmed detection. The case rests on the rotation anomaly, the interior model residuals, and the theoretical plausibility of the scenario given what we know about how massive stars form and evolve. None of that constitutes proof. All of it constitutes a coherent and physically motivated hypothesis that deserves to be taken seriously as a framework for interpreting the star's current state. What the cannibal star hypothesis adds to the overall story is a temporal depth that changes how Betelgeuse feels as an object. It is no longer just a star approaching an unusual end. It is a star with a history, a long, complicated, violent history written in its spin rate and its chemical profile and the structure of its interior, waiting to be decoded by instruments and analyses that are only now becoming sophisticated enough to read it. Siwara's inspiral is not the opening of a new chapter, it may be the closing of a very old book, one that started millions of years ago with a first companion falling inward through a younger, smaller version of the same star, and that ends finally when the last companion completes the same journey, and the system that has survived multiple mergers across geological timescales reaches the one it cannot survive. The star in Orion has been doing this for a long time. We are just now beginning to understand how long. Part 20. The real meaning of the tipping point. We began with a word, tipping point. And after everything we have covered, everything we have built up across the physics of the inspiral, and the debate over the evidence and the three possible endings, and the two competing clocks, and the long complicated history of a star that may have been consuming companions for millions of years, it is worth returning to that word now. Not as a dramatic flourish to close the story on a satisfying note, as a precise physical description of where Betelgeuse actually stands at this moment tonight while you are watching this. Because the tipping point is not what most people imagine it to be. In the popular imagination, a tipping point for Betelgeuse means the explosion. The moment the core collapses, the moment the shockwave tears outward through the stellar layers, and the light from the supernova begins its 650 light-year journey toward Earth. The moment something visible and definitive and undeniable happens, something that changes the night sky in a way that every human being alive at that moment will notice, without needing a telescope or an explanation. That is the tipping point that appears in headlines, in documentary narration, in the casual astronomical conversation at a dinner party, when someone mentions that Betelgeuse is going to explode someday. But that moment is not the tipping point that matters most in the physics of this system, and more importantly, it is not in the future. The actual tipping point, the threshold with the most physical significance, the one that determined the ultimate fate of this system in a way that nothing subsequent can alter, has already been crossed. It was crossed at some moment in the past, a moment we cannot precisely identify, but whose consequences we can measure today in the orbital decay of Siwara, in the atmospheric disturbances of Betelgeuse, in the long secondary period that has been repeating in the brightness record for over a century. The tipping point was the moment when Siwara's orbit descended far enough into Betelgeuse's atmosphere that the drag forces acting on it exceeded any possible restoring mechanism, the moment when the feedback loop locked in, the moment when the rate of orbital energy loss became self-reinforcing and the destination of the system became inevitable regardless of anything that might happen next. Before that moment, the system had options. A sufficiently energetic event, a temporary change in the atmospheric density profile, some perturbation that added orbital energy back to Siwara faster than the drag was removing it, could theoretically have stabilized the orbit or even reversed the inspiral. The window for that kind of intervention, however improbable, was open. After that moment, the window closed. The physics locked in a direction, and there is no mechanism in the known universe that operates inside this system that could reverse it. Siwara is falling. It will continue falling. The rate of that fall will accelerate, and the merger will happen. We do not know exactly when the tipping point occurred. It may have been tens of thousands of years ago, during a time when the only humans on Earth were making tools from stone and watching the same stars without any framework for understanding what they were. It may have been more recent, just a few thousand years ago, overlapping with the earliest human civilizations, with the first written languages, with the construction of structures that we still marvel at today. In either case, by the time anyone on Earth developed the mathematical and observational tools to even ask the question, the answer was already decided. The system was already past the point of no return before science existed to notice it. That is the thing about tipping points in physical systems. They do not announce themselves. They do not come with a visible transition, a change in the star's appearance, a detectable shift in its behavior that would have flagged the moment to any observer paying attention. The tipping point in this system was a threshold in the relationship between drag force and orbital energy. buried inside the atmosphere of a star 650 light-years away, invisible to any instrument that existed at the time it occurred. The universe crossed a threshold of irreversibility and quiet, and the consequences have been accumulating ever since. 2 clocks have been running inside Betelgeuse since long before any of us arrived to observe them. One of them, the nuclear clock, counts down the remaining fuel available to the stellar core. The helium-burning shells, the carbon burning, the neon, the oxygen, the silicon, each successive fuel lasting a shorter time than the last as the burning accelerates through heavier elements toward the iron endpoint that no star can burn through. That clock has somewhere between 100,000 and several 100,000 years remaining on it, with uncertainties large enough that the precise number is genuinely unknown. On that clock, Betelgeuse is old but not finished, approaching the end but not at it. The other clock, the orbital clock, counts down the remaining time before Siwara completes its inspiral and reaches the core region of Betelgeuse. That clock runs on orbital mechanics, on drag physics, on the density profile of the stellar atmosphere, and the mass of the companion and the feedback dynamics of a decaying orbit in an increasingly dense medium. It has approximately 9,000 to 10,000 years remaining, less than 1/10 of the time left on the nuclear clock, and it does not know the nuclear clock exists. It does not slow down or speed up in response to what is happening in the core. It runs on its own physics, indifferent to the fuel supply, indifferent to the burning stages, governed entirely by the gravitational and fluid dynamical mechanics of one star falling through another. When the orbital clock reaches 0, the nuclear clock's remaining time becomes, in the most important sense, beside the point. The merger will have fundamentally altered the internal structure of the system in ways that make the pre-merger stellar evolution models irrelevant. The core that exists after the merger is not the core that would have existed if Betelgeuse had evolved in isolation. It carries the energy and mass and angular momentum of Siwara's entire inspiral, deposited over thousands of years, concentrated in the final stages of the descent. Whatever that merged core does next, whether it collapses immediately or continues burning in an altered configuration for some additional period, it does so as a fundamentally different object from the one the standard models describe. The explosion that eventually results, whenever it comes and through whichever of the 3 pathways we discussed, will not be the death of a lonely red supergiant following a standard evolutionary script. It will be the culmination of a system, a 2-body system that has been locked in its slow-motion collision for longer than human civilization has existed, playing out a drama of gravity and gas and orbital decay that was already written before anyone on Earth thought to look up and wonder what that reddish star in Orion actually was. And here is the thing that stops you, if you let it. You can go outside tonight. Right now, after this ends, you can find Orion in the sky, and you can look at the reddish-orange star on its upper left shoulder without any equipment, without a telescope, without anything more sophisticated than the eyes you were born with. The light that reaches your retina in that moment left Betelgeuse approximately 650 years ago. It began its journey toward Earth before Copernicus was born, before the printing press, before Columbus crossed the Atlantic, before anyone on Earth had any coherent model of what a star was, or any reason to suspect that the points of light overhead were objects of comparable or greater magnitude to the Sun. In the 650 years that light spent crossing the interstellar medium on its way to you, Siwara completed more than 100 orbits inside the atmosphere of Betelgeuse. Each one of those orbits was slightly smaller than the one before it. Each one deposited a little more energy into the surrounding gas, stirred the envelope a little more, moved the system a measurable fraction closer to its conclusion. More than a century of those orbits happened while astronomers on Earth were carefully recording the long secondary period in Betelgeuse's brightness record and explaining it as something internal, something mundane, something that did not require a second star to account for. The evidence was accumulating in the data while the reality it encoded was accumulating in the atmosphere of the star itself. We thought we were looking at a star. We were looking at a system. We thought it was dying alone. It is not dying alone, and it never was. There is a second star inside Betelgeuse, and it is falling, and it has been falling for longer than our civilization has existed, and it will finish falling long after every institution and language and memory of our current moment has dissolved into whatever comes next. The tipping point is behind us. The spiral is in progress. The merger is decided, not a dying star. A system already in motion toward transformation, carrying inside it the accumulated history of millions of years and multiple companions and a feedback loop that crossed its irreversible threshold before anyone alive today was born to notice. And every night you look up at Orion, you're watching it happen. 650 years late, through light that left before we knew what we were seeing, arriving just in time for us to finally begin to understand.